Good afternoon, ladies and gentlemen. Today we will be doing the Algebra 1, Unit 8 review. In this review, we will be covering radicals and also an introduction to the Pythagorean Theorem. So first up, you do have a picture. This picture more specifically refers to the Pythagorean Theorem. So if you think back, the Pythagorean Theorem involves triangles. This right here is a triangle, in which case you have your side B, your side A, and then of course remember that your hypotenuse is your longest side, so it's going to be directly across. You can see that right angle right there, and in my class I remind you that the C is always located directly across from that right angle. And then going through, and pretty much it says the length of one side is 32 feet. Now here's what's tricky about this problem, and I'll help you kind of set this one up but not take it all the way through, is that it says that the sidewalk is a square. So even though it says one of the sides is 32, squares, if you think about it, have all four sides are the same. So if this is a 32, this is also going to be a 32. So if you go into that formula, a squared plus b squared equals c squared, you now have your a and your b, both of which are 32. Squaring each of those and going through and solving that. I do remind you that when you get down here and you get a c equals, you should get 2048. Then to get rid of that square, you will want to square root it and go from there. Now, we will hit the Pythagorean Theorem a little bit later, so I'm going to go ahead and move on and let you finish that problem. Now, first up, this unit, it is very important and critical to understand how to simplify a square root. Now, in my class, we looked at simplifying square roots in two different ways. The first one was to look for perfect squares. Now, you will want to know your perfect squares. At a certain point in life, it's going to be very helpful if you have them memorized. So if you want to practice kind of writing some of them out, perfect squares are always itself times itself. So like 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49, and so forth and so on. So you may want to practice writing those out. But the reason that I draw your attention to this is because when we do simplifying radicals, you always want to check to see if it's any of these perfect squares. And actually in this first example, you'll notice that you got the square root of 36. That is one of my perfect squares. Now, what does it mean that it's a perfect square? It means that I can break that down into a 6 and a 6. Okay? And sure, you could keep going with the factor tree and keep factoring it, but now all of a sudden I have a pair of 6's, which means my simplified version is just 6. Now, I do want to remind you, quite frequently people struggle with when to have the square root and when not to have the square root. I want to remind you here that the square, or when does it come out of the square root, is when it changes. Or you could say when you find that pair. So right now I found a pair of 6's, which means that 6 gets to come out of the house. Now this leads me into my next problem. In my classes, I remind you that I kind of gave you two options. You could either try to find a perfect square inside of 196, or sometimes it's just as easy to start breaking it down. So if you start doing a factor tree, this goes back to the last unit, you can pick pretty much any numbers as long as they multiply to 196. So I'm going to start out by picking 98 and 2. 98 times 2 gives me 196. So I haven't changed the value. 2 is prime, so I'm going to go ahead and circle it, and I'm going to keep breaking down 98. This time maybe I do 49 and 2. Again, there's a prime number, so I circle it. Now 49 is not divisible by 2, so I can't break it down into a 2 and something, but I could do a 7 and a 7. Now that I've finished my answer, I want to go back and say, do I have any pairs of numbers? Well, here's a pair of 7's, and look at this. Here's a pair of 2's, right? So I have a pair of 7's. That pair of 7's gets to move out of the house. I have a pair of 2's. They also get to move out of the house. And then whatever's left inside the house would be anything that didn't have a pair. Well, everything here had a pair, so I just had my 7 and my 2, which says that my final answer is 14. Now, if I do this same method with 27, and I break this down maybe into a 9 and a 3, 9 keeps going, 3 and 3. Then I go back and say, where's my pair? Oh, well, wait a second. I have a pair of 3's. So that means I get to pull a 3 outside of the house. But then look at this poor little 3. He doesn't have a partner, right? He didn't have anyone to pair up with, so that is when he has to stay in the house. So when you're trying to decide what stays in the house and what doesn't, that's kind of where you need to go off of. Does it have a pair? If it has a pair, it gets to move out of the house. If it doesn't have a pair, it has to stay in the house. So just keep that in mind. I would continue with the factor tree for some of these other ones. If you recall any of the ones with variables, I would highly recommend you write out how many you have. So I have 2 x's, I have 5 y's, 3, 4, 5, and 7 z's, 2, 3, 4, 5, 6, and 7. Then go through and say, what type of pairs do I have? Well, here's a pair of x's, here's a pair of y's, here's a pair of y's, pair of z's, z's, and z's. Keep in mind that this y and this z did not have a partner. So when I go through, I had 1 pair of x's, so I can take 1 x out. I had 2 pairs of y's, so I need a y2. And I had 3 pairs of z's, so I need a z3. Then going back and saying who did not have a pair, this y did not have a pair, and this z did not have a pair, so they have to stay in the house. Now sometimes you're going to have both numbers and variables in one. Don't worry, deal with the number first, then do exactly what we talked about with the variables over here. Now I do want to point out that this is 100, so you could do the tree will always work, or 100 is actually one of our perfect squares. It is 10 squared, so the square root of 100 is simply a 10. So you don't even have to do a tree for that one. If you notice it being one of the numbers listed up above, then you can know that you don't even have to do a tree, just kind of factor it. Now, the next rule that we run into is multiplication. I want to remind you that when you have multiplication, anything in the house can be multiplied and anything outside of the house can get multiplied. So in this case, both the 8 and the 12 are inside the house. So I can go ahead and multiply 8 and 12 to get 96. Now I stress to you that's still in the house. Multiplying 8 times 12 doesn't take it out of the house, it just makes it one house. And now with the 96, you're going to want to kind of break that down very similar up top here. 3 and 20 is going to be the same as what you did in H. So I'm going to go ahead and move on to the next page. The next page is interesting because you have 3 division problems, one of which says to rationalize. Okay? Here's the difference. When you're just doing straight up division, you're just going to want to reduce those fractions. So 72 over 50, I could maybe pull a 2 out of both of those. That's going to give me 36 over 25. Now, you may be thinking to yourself, now keep in mind that's still in the house. Think back to the multiplication. Just because I multiplied it doesn't mean that it got to move out of the house. Just because I simplified this doesn't mean I get to move it out of the house. But what's really cool is you are allowed to break it up into 2 pieces. Now take a look at this. You have a 36 and a 25. 36 and 25 is in my list. Therefore, they simplify into nice whole numbers. Square root of 36 becomes 6. Square root of 25 becomes 5. That's your final answer, nothing left in the house. Now with k, you are absolutely allowed to simplify, just like you did over here. Or, again, pause, think back to your list of perfect squares. Now, we have 100, and actually 11 times 11 is 121. 12 times 12 is 144. Look, here's 100, here's 121. Those are our 2 numbers here, 100 and 121. So just go ahead and split those up. Square root of 100 is 10. Square root of 121 is 11. Boom. So if it's one of those numbers on your list of squares, like the squares up front here, if it was one of those numbers, you can go straight into your answer. If it's not, that's when you're going to want to do the factor tree. Now, rationalizing. How is rationalizing different? Rationalizing is different because the 7's on the outside and the 13's on the inside. Let me go ahead and make this a little bit bigger. So the 7 is on the outside, the 13's on the inside. That means I can't just go into straight division like we did over with these other problems. But I also cannot have a square root in the bottom. So how do I get rid of that? By simply multiplying it by itself. Now on the top, the 7's on the outside, the 13's on the inside. They're unfortunately not going to mix at all. It's just going to have to stay 7 square root of 13. But this one, think back to the multiplication on this front page, okay? You can take 13 times 13 and get 169. 169 should be on our list of perfect squares, which means, again, the top stays the same, but the bottom, the square root of 169 is 13, and you're done. Now, I do want to remind you with n also says to rationalize. Sorry, m. M says to rationalize. N says to rationalize as well. So again, all of these, you need to multiply top and bottom by that square root. Top and bottom by that square root. Now, the only difference with n is you are allowed to simplify anything on the outside of the house. So, for example, this 3 and that 30 could be simplified to become 10 over 1. But that square root of 5 is still in the bottom. So keep it there and deal with it after or before you simplify. It's up to you. Moving on to the last types of problems involving really square roots is the adding and subtracting. I remind you, adding and subtracting can be very simple as long as all of the houses are the same. So when you find your answer, it should also have a square root of 6. That does not change. But what does change is taking 1 minus 3 plus 10, you should get 8. 1 minus 3 plus 10 gives you 8, and then that square root of 6 stays the same. In the cases as such with P and Q, the houses don't match, so try breaking them down first. So for example, I could break this down into a 3 and 100, maybe a 10 and a 10. Well, look at that, there's a pair of 10s. You should know that because 100 is one of our perfect squares. So this particular problem could become, there's a pair of 10s, so the 10s move out. The 3 was all by itself, so it stays in the house. So this piece becomes a 10 square root of 3. Now here's what's hard about problems like this, is it's very tempting to see this square root of 10 and this 10 and be like, oh my gosh, they match up, that's great. But keep in mind this square root of 10 is inside the house, this 10 is not. And then taking us down to our last couple of problems. These are the Pythagorean Theorem type of problems. So as long as you're familiar with the a squared plus b squared equals c squared, you should be good. A reminder that c is always located directly across, and then your a and your b are just your side numbers. So for example, you'll have a 9 squared plus, you can call it b or x, it doesn't really matter. B squared equals c squared, which is 100. Solve this all the way through, you're going to get 81 plus b squared equals 100. Subtract 81 from both sides. You're going to get a b squared equals 19. Now here's where it differs a little bit. With all of these problems up above, you should never get a decimal. You can get fractions, you can get numbers with radicals in them, all that, but you should never get a decimal. With these Pythagorean Theorem problems, you should get a decimal. Not always, not 100%, but I encourage you to get decimals. If you get a decimal, you're perfectly fine writing it. So for this one, I got a 4.36 as my b value, and that will be my final answer. So this is the only section that you can get decimals in. All the other sections, you should just be simplifying. Henceforth, why the directions say simplify, I want it to still have a square root in it if it has to. I do not want decimals here. If you simply type that in and get a decimal, you will be marked wrong. But these ones, you can absolutely get a decimal. There is no problem with that. Going on to the back side, again, some more Pythagorean Theorem problems. And then these last ones are still the Pythagorean Theorem with the a squared plus b squared equals c squared. But they're giving you 3 numbers and asking you, does it work? Reminder that c is always your biggest number. So this one has to be c. Square that. Calculate these, you get a 9 plus 16 equals 36. Add those together, you get 25 equals 36. That does not work, and therefore this is not a right triangle. So for the rest of these, again, identify the biggest number. That's going to be your c. Plug it into this formula. See if it works. If it does, then it's a right triangle. If it does not, it is not a right triangle. Alrighty, good luck on your test.